When you're coding in C, there's this one type of bug that's, well, it's sneaky. It doesn't crash your program, it doesn't throw an error message, not at first. It just creeps in, silently eating up your system's resources until everything just grinds to a halt. So today, we're going on a hunt for this silent predator, the memory leak. I mean, think about it. Most bugs are loud, right? They're obvious. A memory leak, though, it's completely different. It's a slow burn, like a ticking time bomb hidden in your code that can make a program that seems perfectly stable just fail completely out of the blue. So how does this invisible threat even work? All right, so here's our game plan. First, we're going to break down what a memory leak actually is. Then we'll get into why they're so dangerous. After that, we'll look at the common coding traps that cause them, and most importantly, how to prevent them. And finally, we'll arm ourselves with the tools to hunt them down and fix them for good. To really wrap our heads around this, let's use a simple analogy. I want you to forget about code just for a minute and picture this in your mind. Okay, so imagine your program is this super busy worker sitting at a desk, and to get anything done, it needs paper, lots of it. And all that paper is stored in a giant drawer right next to the desk. That drawer, that's your computer's memory. So whenever your program needs to store a piece of information, it opens that drawer and pulls out a fresh sheet of paper. In the C language, we call this memory allocation, and we do it with functions like malloc. Pretty straightforward, right? Now, a well-behaved, tidy program, once it's done with that piece of paper, is supposed to put it back in the drawer so it can be used again. This is called memory deallocation, and we use the free command for that. And trust me, this is the most crucial step. And right there, that's it. That's the whole problem. A memory leak is when your program takes a piece of paper, uses it, and then just tosses it on the desk and forgets about it. If you do this once, no big deal. But do it 1,000 times, and pretty soon your desk is buried in old paper, the drawer's empty, and your program has nowhere to work. So to put that in more technical terms, a memory leak happens when your program dynamically allocates a chunk of memory, but then completely fails to release it back to the system. That memory becomes orphaned. The system still thinks it's in use, but your program has lost the pointer to it, so it can never be accessed or freed again. It's just wasted space. Now, a few forgotten pieces of paper might not sound like a huge issue, but imagine this happening thousands of times a minute in a server application that runs 24/7. The consequences can be absolutely devastating. Let's dig into why this silent predator is so incredibly dangerous. You can really see how this spirals out of control. It starts with simple resource depletion. Your program is just hogging memory it doesn't need. This very quickly leads to performance degradation, where not just your app, but the whole system starts to feel sluggish. And the end game? Total system instability. This is where you get those bizarre random crashes that are an absolute nightmare to debug. Okay, so we get it. Leaks are bad. Really bad. But how do these things actually creep into our code? Let's go ahead and investigate the usual suspects. All right, let's run through the common mistakes. The most obvious one is just plain forgetting to call free-o, but some are way more subtle, like losing the pointer. That's like dropping the only key to a room you need to clean. You can never get back in. Then there's improper reassignment, which is a similar idea. That fourth one, errors before free-o, is a huge culprit. Your error handling logic accidentally jumps right over your cleanup code. And oh man, leaks and loops, those are particularly nasty because they can chew through your system's memory at an incredible speed. Okay, that's enough doom and gloom. Let's talk about solutions. The great news is that with just a little bit of discipline and some good habits, we can build a really strong defense against memory leaks. If you only remember one thing from this whole explainer, please let it be this. This is the golden rule of memory management in C. For every single malloc, there must be a matching free. Think of them as a pair. The second you type malloc, your very next thought should be, okay, where and when am I going to free this? This is a fantastic way to see the difference. On the left, you've got the leaky logic. It hits an error and just bails, leaving that allocated memory completely orphaned. But look at the safe logic on the right. An error happens, and what does it do? It jumps to a dedicated cleanup section, makes sure free gets called, and only then does it exit. This way, no matter what happens, you always clean up after yourself. And here are a few more pro tips for you. Always free the old memory before you reassign a pointer. Be absolutely meticulous when you're cleaning up complex data structures like linked lists. You have to free every single node. And honestly, one of the best tips is this. If you don't have to use dynamic memory, don't. For variables that only exist inside a function, the stack is your best friend. It cleans itself up automatically. So even when we're trying our best, a leak can sometimes slip past us. It happens. So when it does, how do we find it? Let's open up the toolkit and look at the best ways to detect and fix these hidden bugs. So what's in our arsenal? Well, your first line of defense is always a good old-fashioned manual code review. But for some real firepower, you have tools like Valgrind. It's an absolute legend in the C community for sniffing out memory problems. Modern compilers also have amazing tools built right in, like Address Sanitizer or ASAN, which is super fast and effective. You can even get creative and build your own simple counters to just make sure your malloc and free counts always match up. And that brings us to our final question. Your code might run perfectly today. It might pass every test, but is it silently leaking memory? Remember, memory leaks are the predators that can bring down even the biggest, most robust applications over time. The key is to be vigilant, to be disciplined, and to use the right tools to make sure your code isn't just working, it's clean.